Mm, What's up? In this video, I want to go over some worked examples as we get with pure substances. This is a follow-up video for pressure cookers that I did go over. I posted it a couple of minutes ago. So in case you didn't watch it, you could go back and you watch it. Uh, it could be quite helpful. I did discuss I did discuss uh, ideas about pressure and temperature and how they affect cooking and the solution of a pressure cooker as engineers. Okay, so for this video, I'm working over some examples. Let's get started. So the example one is pressure of a circulated liquid in a tank. So the question goes: a rigid tank contains 50 kilogram of saturated liquid water at 90 degrees Celsius. Determine the pressure in the tank and the volume of the tank. So for these questions, the first thing you want to do is interpret the question correctly and know what the given values rhyme with and what they mean. So in this question, the first thing you really notice is rigid tank. And this in thermodynamics, it translates for or there's no change in volume for that tank. Its change in volume is zero. It contains 50 kilograms of saturated liquid water. So mass is equal to 50 kilogram, and 50 kilogram is for the saturated liquid water at a temperature T, which is equal to 90 degrees Celsius. So determine the pressure in the tank, which is P, and pressure in the tank is always uniform. You're not going to be asked to look for P1, P2. No, the pressure within any singular tank or in a singular system, usually for these pure substances, is usually general and uniform. And I want the volume of the tank. The mass, the change in volume, but the volume. Okay, it's a rigid tank, but it has a volume, but it has not change in volume. So I want that volume, capital V, not a specific volume, but this is the capital V. So you have to differentiate between a specific volume and volume, total volume. Another one, total volume, which is capital T. So, and another interpretation you want to make, that is from this next line as you do the solution. The next line is what table you have to use to answer this question. And in this for this question, we're going to use table A4. Now the most wise question is, well, the property tables and charts have tables from A1 to up A something like 23. How am I going to know the right table to use? Well, the most correct answer is it's given in the question. What table to use is specified, but what properties is being talked about in the question. So, for instance, this time they'll say that circulated. Once you look at the word circulated, liquid water, you know you have to look for a temperature table A4 or A5. You will use table A4 if the given property is temperature. That's why you have circulated water temperature table. So if the specified property is pressure, if it gave a situation pressure, you would have to use table A5, which is circulated water pressure table. So now we're going to use table A4 because it gave us temperature T is equal to 90 degrees. And because they said the mass that was given, this mass is of circulated liquid. That means this 90 degrees Celsius is the temperature at which water was became circulated. And And I want to see whether they can give you this definition of what saturation is. So, by definition, saturated uh, saturation temperature is the temperature at which a pure substance, e.g., water in this case, changes phase. So that means for this specific question, they're telling us at 90 degrees Celsius, if you were boiling water, it would change from, it would hit the circulation line, you know, is at a point it's going to start boiling, you know, changing phase. So now that means you know that this 90 degrees Celsius is equal to circulation temperature, which is equal to 90 degrees. So from there, you interpret that you have to use temperature table A for, and how are you going to use it? Well, you're going to, you don't have to like put this in your solution, but I had to extract those screenshots of temperature tables, and I extracted for you to show you and guide you how it's used. But once you're in an exam, you just have it like practically with you. So you just copy the values and you plug them in the answer without putting maybe the screenshot of the temperature tables, because that would be a lot of work actually. So let's go ahead. You've been given temperature as 90 degrees Celsius. So you're gonna come to this temperature table, which runs from 0.1 up to some bigger temperature. I just cropped it out, so it's not the last one. It's not 95, it's the last. There's more temperature values, but we are mostly interested in this value that I've highlighted, which is 90. And at 90, we see the saturation pressure at 90 is 70.183 kilopascals. So you have P is equal to circulation pressure at 90 degrees Celsius, which is equal to 70.183 kilopascals. And that's your first answer. You've passed the first part of the question. And it's something that's very good for you to know. The interpretation of this. What does this mean? Uh, in thermodynamics, and for you as an engineering student though, this means that at a pressure of 70.183 kilopascals, water is going to boil at 90 degrees Celsius. Actually, in the previous video about pressure cookers, I did explain this misconception about boiling, what temperature water boils at. You know, when you say water boils at 100 degrees Celsius, you're totally wrong. You're incorrect. So you want to check that video and know why. Okay, I would save you the burden and tell you now, but you have to check the video and you know why. Hmm? So this is the first part of the question. They asked you for pressure, we found it. Now we have to look for total volume. So and we're going to use this table also to find it. So how are we going to do that? So at that circulation temperature, we also have circulation liquid, you know, specific volume of the circulated liquid, which is given by 0.001036 meters cubed per kilogram. And we know that total volume is equal to specific volume times total mass of the liquid. Okay, and what does specify liquid? Because we still have a liquid. We don't have a component of circulation yet because we didn't talk about it. So you multiply total mass with a specific volume and you get your total volume of the tank, which is equal to that. And of After you've done that, most questions will ask you to draw the schematic diagram or the TV or characteristic graph, and this question is going to appear like this. And the interpretation is we have a circulation temperature as 90 degrees. So for temperatures below 90 degrees, they will change the temperature of the water. They will increase it along this line. And when that one's for that specific pressure, 70.183 kilopascals, any temperature below 90, it is going to just increase the temperature of the water. And once you hit the temperature of 90 degrees Celsius, the water is going to start, it's going to hit the boiling line, which is the saturation line. And once you keep the temperature sustained for some time, the water is going to vaporize till it hits the saturated vapor line and the superheated vapor along that pressure. Yeah, that's the specific interpretation. And why was the TV diagram? Because we're doing everything at a constant pressure. So you know that whatever is changing is the temperature and the specific volume. And this is not total volume. This is small v, which is specific volume. So let's go over for example 2. Example 2, temperature of circulated vapor in a cylinder. So the question goes, a piston cylinder contains 2 feet cubed of circulated water vapor at 50 psi pressure. Determine the pressure and the mass of the vapor inside the cylinder. And this is a tricky question. The trickiness within the question is not the calculation, but is the interpretation of the question and its units. Everything here is given in English units. You see, you have feet, you have psi. So, in case for most people, for the book that I was using, it has the conversion. It has a extended version, of the temperature of the property table that covers everything in English units. So you don't have to do the conversion that I did for this example. But for most people, for the people I made this video, I said it could be possible you don't have that table because what I was trying to Google online to find it was quite hard. I had to barely like re-download the actual textbook. The one textbook I was using. It's the only thing that I would get that had the property tables for stay for property table that had English units. And what did that tell me? That told me that you shouldn't rely on that because it means most people out there won't have that property table that has the English units. So the best idea was to convert these units into the more normal standard units, which is pascals. And yeah, for the physics base we can use, but this we had to convert it, and we should look at how we did that. So for pressure, 50 psi, to convert it, we know that 1 psi is equal to 6.9476 kilopascals. So you multiply. Now let me look. Let me see if this value is over the scientific calculator. Let's shake that. Be sure. Oh, I don't see it. I don't see it. I don't see it. Yeah, the scientific calculator does not have a value, but that's the actual value, 6.9476 kilopascals. So you will convert the pressure from English units, 50 psi, to 344.738 kilopascals. At least you can deal with the feed, but this, you know, the value of pressure matters a lot, so you have to know its actual number. And if you had, actually, I will redo this number later on. I'm going to redo this number, but using the English units table. So in case you have a table it's covered in English units, you don't have to go over this, the conversion. You maintain the units is given in the question and you work it out, just like the previous example. So now, what table we're going to use? Table A5, saturated water pressure table. The question is why? I already did experiment how we find out what table to use, and I'll go over there again. This question says circulated water vapor, and the situation part. Once you see the word saturated, you already know what to use. It's table A4 or A5, and the 4 or 5 depends on what property is being given. This time it's pressure, so we have to use A5 because it's the pressure table. And it's right here. You see, saturated water pressure table. It gives pressure, and the values that follow. So the pressure was being given is 344.738 kilopascals, but from the table we don't have such value. So the value we have, it lies in between 225 kilopascals and 250 kilopascals. It lies in between here. So what we're going to do, we're going to use interpolation. And for neatness, it's a good idea that you draw this table within. You don't have to put this table, this one here, you don't. But for this, it's good. It's a good. It's a neatness motive to draw it, just like how I drew it here, and you put this first one, first value of pressure in kilopascals, which is 925, and the temperature that goes with it, which is 136.2527 degrees Celsius. And now you put the value which you have, which is 344.738, and the temperature which you want, and then this other value which is slightly above the given value with 250 and 138.86. And now how does interpolation work? Interpolation works that you get the required value, you subtract it from you get this lower value here. You subtract it from the value you need. The theory is this temperature that you don't know about. You quite certain that since this value is greater than this but lower than this, the temperature here must be greater than this but lower than this. That's why you subtract. You see here, you don't know the actual value of T, but you know mathematically and guessing, you make an educated guess, the temperature must be greater than this, but lower than this. So you get the temperature minus that, you divide by this minus that, the pressure that corresponds with this temperature minus the pressure that corresponds with a temperature. And you equate it to this, this minus this. And the pressure that corresponds with this minus that. And the temperature you get is going to be the saturation temperature, which is equal to 138.31 degrees Celsius. And why is it the saturation temperature? Because they told us we have a saturated water vapor. So that means that at the pressure of 244.78 kilopascals, we have a circulation temperature of 138.3831 degrees Celsius. And that's your first answer. And what else are we finding? We want temperature, we found it, and we want mass of the gas or the vapor. So let's find that out. So to find the mass of the gas, you would want to use interpolation again. So now what do? You come back. Remember, we were finding temperature, so we picked the value of what we know of pressure and temperature. Now we're going to pick a value of pressure because of the values of pressure we have them. And 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 the value of specific volume, you see. So you're going to pick a value of specific volume and pressure, but still the value of specific volume we don't know it, so we're going to do interpolation again. You pick these two and these two, see, of the vapor, and it looks like this. So you do the subtraction just like we did here, and you get your answer as 0.53217 meters cubed per kilogram. But we have a problem. And you could be like, what's the problem? Well, the problem is we are not using a temperature table, a properties table that has English units. So whatever we're calculating gives us the standard units, meters cubed or kilogram. But we have feet in our question. The question gives us a total volume in feet, so you have to convert. And I know the conversion is not an easy thing for everybody. So for those who can access the English units table, I will redo the question. And once I redo the question and upload it, I will paste the link to that video within the description of this very video, such that you could just skip over that conversion part and you go to the direct use of the English, the property tables that has the English in it. But for now, for those who don't have, you have to learn how to do the conversion. And it's done just like this. You have your value of a specific volume of the vapor phase, which is this 0.53217 meters cubed per kilogram. So now, but we know one, and where the conversion becomes a tricky thing is the power of the unit that you're converting from. So we're converting these meter cubed to feet cubed. So the actual conversion unit of 1 meter is 3.280839895. But now we're dealing with meter cube. So you're going to cube this entire value and you cube that entire value such that these units can cancel. If you be like 1 meter is equal to this feet and you don't cube the value, you are wrong. So you get feet cubed and the meter cancels, and we know that 1 kilogram is equal to 2.20. No, that's a long reading. It's 2.2046224761 IBM. That's pounds. So the kilograms cancel, and once you do the calculation, you have 8.52455 feet cubes per 1 BM, IBM, which is pounds. Now you have your value in feet per pound, but we want the value for the mass of the vapor phase, and from this equation, which is specific volume, mass of vapor phase, and the total volume of the vapor phase. And once you do that, you can rearrange and you get that answer. So I think we answered the whole question, and the answer will be in pounds. Okay, so the tricky part in this question was about here, this cubing part, and having a conversion table for these, the pounds and the kilogram, the meter and the feet. Yeah, it's a lot of work. One thing that I did do is I went online, Because to enter into a thermodynamics paper, you are allowed to go with your property tables. So one thing that I would advise you to do is go online and you get the actual conversion rate of most of the units you're going to use, and you create a own table and you fill them in, and you can print out that paper and you attach it to your properties table. That will make your work much easier once you go for the exam. So I'll go for the next example, and this one is a fill out, but it doesn't look easy as it sounds. Once you tell you fill out, oh, you'll be like, okay, a simple one is coming, but yeah, it doesn't look simple. It's not actually simple like it looks. So they're telling us to use of steam tables to determine properties. So determine the missing properties in the first description in the following table for water. We have temperature at degrees Celsius. We have pressure at kilopascals. We have internal energy, actually specific internal energy. How do I know it's specific? Because it's a kilojoules per kilogram, and again, it's small units. And we have the quarterly concept. So once you don't know any of these, for instance, what the quality concept means, I already did explain that in some previous video way back. I think it was one of the first videos I uploaded about thermodynamics. So you just check the playlist because they're all in entire playlist. In case you're watching this video as a random video on your feed, you could check out the playlist. How would you find that? You click in the description or you visit you know, the dashboard of my YouTube channel. You will see the playlist that right there, and you could watch everything you need to know. Because I've covered it already. And because you're watching it through a playlist, yeah, you could testify that it's true. Okay. And I usually try to copy all the links to those videos into the same video that I tell you about it. So let's go on. So to answer this question, you will have to retype this table, and then you fill out the missing work. You know. So let's start with row one. And row one, they've given us the value of the quality concept, and the quality concept is equal to x. They've told us is 0.6. What does that mean? It means that 60% of the mass, 60% of the mass is in vapor phase, and 40% is in the liquid phase. So thus, the phase is circulated liquid vapor. It's a two-phase vapor. It's a two-phase mixture. So you know that this pressure here, which is given, is the saturation pressure, and that will make our work even much easier. So we go straight to table A5. In case you still don't understand why we are using table A5, we are using table A5 because we have found out that the pressure that we has been given is the saturation pressure, because the mixture we're dealing with lies within the circulated liquid vapor phase. Okay, and the table that is corresponding with that is table A5. Why table A5 and not table A4? Because we have been given a property of pressure, and that table covers pressure specifically. So it's right here, circulated water pressure table, and the pressure we was given is 200 kilopascals, and you see I've done all the work, for you. It's highlighted right there. So pressure 200 kilopascals. It resonates with a temperature of 120.21 degrees Celsius, which is right here, and it's the saturation temperature. And there you go. You finish your part one, but that's not the only work you have to do, because you have to fill in temperature, specific internal energy, and you describe the phase. And whenever you describe the phase here, circulated liquid vapor, you could say circulated mixture or two-phase mixture, two-phase liquid vapor phase, that's the description the one. And the temperature is 120.21 degrees Celsius. So now we want to describe to find the next requirement, which is the specific internal energy. And now from the specific internal energy two-phase formula, which is given here. And in case you really have a problem with, I don't know how that formula comes about, could you explain that? I already did, you know, I already did in some previous videos. I did upload on my channel some time back. We're back. So in case you want to know that, you can visit that channel, officially, and you look out for those videos. You will find them and you will use them, and they'll be of great use. So let's go, get going. So you're going to come back to your table at 200, and you look for specific volume of the saturated liquid, which is here, 504.50. And you have this concept of, which is the difference between the specific energy of the vapor phase minus the specific volume of the liquid phase, which is 2024.6. You know, this resonates with some, yeah, bro. So you have the quantity concept, which is 0.6, and you multiply and you get your volume. And don't forget the units, which is kilojoules per kilogram. You are done with the first part of the question. We got to row 2. And within row 2, they've given us temperature of 125. They've not given us pressure, and they've given us specific internal energy, and they want to do the rest. So let's do the rest like we are asked us to do. So the given values are here. So from table A4, examine. Now here comes the problem. They're just giving you temperature and internal energy. There's no way by any means that these two things they've given you can ever tell you what type of mixture you're working with. There's no way. It's just giving you temperature and internal energy. And you cannot be like, I'm going to go to the table and I'll start looking, because no, 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 no. There's a hell lot of numbers. This is just like a fraction of what the tables look like. Oh my God, there's so many numbers and so many pages. So you're not going to go through looking for the value of internal energy at 160, and you'll be like, oh, where is it? Where is it? Oh, no, that is going to be a lot of work for you. So what do you do, and why? How do you know that you have to use table A4? Well, examining the properties of a substance at its saturation point is easy. Okay. So what you do is, once you get such a question, you're going to examine the specific internal energy of the liquid phase and the specific internal energy of the vapor phase at that temperature they've given you, and you compare it with the given internal energy, specific internal energy. So, and you have to remember this property. Once this internal energy that has been given is less than the specific energy of the liquid phase from this table, that means you're dealing with a compressed liquid. Once that is greater than the specific energy of the vapor phase, that means you have a superheated vapor. And once you have it lying in between the two, you're dealing with a circulated region of the two-phase mixture. So let's go going. Table A4 is right here, and we have a temperature of 125, and UF is right here, and UG is right there. So you copy them, and now you're going to realize that 160 lies in between. So the first description is circulated two-phase mixture, or you'd be like two-phase liquid vapor mixture. So The temperature is this, and it's saturation temperature. So you just copy the pressure that is that corresponds with the temperature, and it's right here, 232.23 kilopascals. So in case you didn't understand that, how I did get that, I would want to repeat it. You examine the property of these two and you compare it with this at this temperature using the saturated water temperature. And now remember we have also described the quality concept, and you could find the quality concept from this formula. I also did derive this formula some time back, you know, and the video is also uploaded to my YouTube channel so you can check it. And once you do that, you have a value of 0.535. Did I say that correctly? 0.535, yes. Okay. And the quality concept has no units because you're dividing specific volume with specific volume. So, you know, the units cancel. So we got to roughly, row 3. Giving us a pressure of 1,000 kilopascals. This is equivalent to 1 megapascal, an internal energy of 250. And this is way much similar to this, what we've just done right here. Only that now they've given us pressure and internal energy is the same, very similar. So what do you have to do? For someone that has really been following, they already know what to do now. You cannot tell whether it's superheated, whether it's compressed liquid, whether it's a two-phase mixture. What you have to do is just have to examine this property at this pressure. Once you find that the internal energy you get is lower than the specific internal energy of the liquid phase, you know you have compressed liquid. Once it's greater than the specific energy of the vapor phase, you know you have a superheated vapor. Once it lies in between, you know you have a region within the two-phase mixture. So we go to table A5. And someone, please, you should by now know why we're using table A5. We're using table A5 because we have been given pressure. And this is a pressure table. And we've been given 1,000 kilopascals. And it's right here. And now you get the value of your internal energy, which is, right, what is it? Internal energy. It's right here. You see? 252, 250 is 2000, 2582.8. That's for the vapor phase, and for the liquid phase, it's 761.39. But the value we've been given is 292,950. So, and this value is greater than the value we've got for the specific internal energy of the vapor phase. That means the phase is superheated, the mixture lies within a superheated region. So it's a superheated vapor because this is greater than this, and this is the value of the vapor phase. So from there, so I hope now you get the idea. This was a test. And why do we test using the saturation table? Because it's convenient. Okay, it's convenient. Now we actually know that the table we were supposed to use in the first place is table A6, but we would not know without using this first. So you have to go to use this first. You find out, and now we're here using table A6. So we're asked to find the temperature. Okay. So you come to table A6 and you look for the pressure that's being given, and the pressure that we have is 1 megapascal. And for the situation to happen is 178, but we won't need that. So you're going to look for the value of the internal energy that you've been given, which is 2,950, and it's not here, but it lies in between here. So you're going to use interpolation, use temperature, and these two known values, and you find the value of temperature, just like we did here. You see, this is the first value, it's right here. Then you put what you already know, and then you put this other one. You calculate, and you, oh well, sorry, I wasn't supposed to put X. Can I edit that? It should be T, because X means quality. Yes, it should be T, okay. And you get a temperature of 395.19 degrees Celsius. Yeah, and you're good to go. Now you have found the answer for the phase, which is the vapor phase. You found the temperature, and you have to find the quality. But you cannot find the quality concept for this because it's not applicable. Why? Because the quality concept only applies for a saturated liquid. Yeah. The reason I also already gave it in some video back. Okay. Well, after deriving the formula, we did the interpretation of that formula for the quality concept, what it means, and we did explain that. And okay, maybe to give you like a brief highlight, the quality concept is the ratio of the specific of the mass of the vapor phase to the total mass. So we're dealing with superheated vapor in this example, and there's no phase in liquid or mass, so we don't have a quality concept. We don't have the values to use to calculate the concept value. And we know the quality concept should lie between 0 and 1. Okay, so we go for low 4. And we've been given temperature at 75 degrees and pressure at 500 kilopascals, 0.5 megapascals. So again, now you don't know whether it's a compressed liquid or circulated mixture or superheated vapor. So you're going to check for circulation, just like we do, okay? Just like we do ours. So what do you do? You so you come to your table 5 pressure table. You look for 500 kilopascals. It's right here, and you check whether the temperature is resonating with this. But the temperature, the solution temperature, once you have a pressure of 500, is 151.85 degrees Celsius. But now we have this. But from the properties of all these, we know that when compressed liquids, like something you haven't started boiling, okay? They're usually at greater pressures and very low temperatures, okay? Think of water you haven't boiled, okay? It's at a greater pressure but very low temperature, and that's what exactly we have here. The pressure is so high and the temperature is so low, so you know for sure because this temperature is lower than the circulation temperature we've got from the saturation table. Thus, the phase is compressed liquid. Compressed. It's compressed, okay? But we have a problem. After finding this from the circulation table, you have to come to table A7, which is the compressed liquid table. And you will find that at 0.5 megapascals, there's no values for this. This pressure is so low, it's too low for compressed liquid, and it's what we've been given. We've been given 0.5 megapascals, but for compressed liquids, they usually go beyond that pressure, so maybe 10 megapascals or what. So we cannot use the compressed liquid table. What we're going to use is we're going to use the circulation temperature to find the internal energy. And at 75, which is here, you will get the internal energy of the liquid phase to be this. Put its units, I forgot to put the units. And okay, by interpolation, which is this and that, oh, before you go for the interpolation, okay, you will first find the value of later. I think I did put a diagram. Yeah. I'll explain what we are doing right here. But now first follow up. The value of the internal energy of the liquid is specific internal energy is this 313.99, which is that. Put the units. Can I put the units? Oh, I can edit the thing again. Oh, I can. Oh, can I? Yes, I can. Kilojoules per kilogram. So by interpolation, now that's the first step. But remember, we were given a pressure of 5, no, a pressure of 500, and we found that the saturation temperature is 151.3 degrees Celsius. So we used this temperature first, 75, to find the internal energy of the liquid phase. But now we have to find the property at the saturation temperature, which is right. Did I copy it out? Which is, you see, it's right here. And how did I know that? From the table there, we had a value of circulation temperature to be at 151.83. So we know that it lies in between here. So you do interpolation, use temperature, and I think this is pressure. Is it pressure? Let's shake. Oh, yeah, pressure. We're trying to find the pressure which is working, and that's the temperature. So now, this is the graph of T and specific internal energy. So at 75, you realize the 75 temperature, it does not hit the saturation line. But now this temperature we found later is the one that will allow circulation of the liquid at this pressure. And there you have it. So we go to, and the quality concept is not applicable because below here, the quality concept does not work. The quality concept to be, for the record, works for things that are lying under this dumbbell shape, you know, and beyond here it also doesn't apply. So you have the first description is the compressed liquid, and now we have law 5. That told us the quality concept is equal to 0.00. And now using this graph I can show you what that means. Here we say the quality concept here does not work. It's not zero. It's not zero. It's something below zero. It does not work. It's not applicable there. But once they tell you it's zero, that means it's along this line here. Okay. And once you calculate, you find the quality concept is equal to 1. You find that means it's right here. The substance is lying along this line. And I did cover all this before, you know, in the videos I've been telling you about. But to specify, the whole point is we've been given a quality concept of 0, and it's along this line. The mixture is along this line. It's not yet started vaporizing yet, so it's a circulated liquid. So from this, as volume, once you know that the quantity concept is zero, you're going to find the liquid, the volume is only in the liquid phase, and they've been given a temperature of 850 kilopascal saturation temperature. This line is the saturation line, so you know that liquid is in the circulation liquid phase. And use temperature table, pressure table A5. We have looked at why we're using this table. So at this pressure, 850 kilopascals, it's right here, and the temperature is there. You just copy it, and that's your answer. And the internal energy is given here, 731.00 kilojoules per kilogram. And since it's only, the mixture is made of only liquid, that will correspond with the total, is equal to 731.0 kilojoules per kilogram. And you could also use this from this formula. We know it's zero. Once you multiply by 0 you will get that, and it will work exactly the same way for the internal energy, and that's your answer. So we have to fill out the answers that we said. Can I edit? Yes, I can. So the first question, the wanted temperature. We found the temperature as what? I just copy from my work. Okay, the first temperature we got was 120.21, and the internal energy was 719.26, and the first description was circulated liquid. Oh shit, what's that? Liquid vapor phase. Oh, you just put this in brackets, or you ignore it. You'll be like saturated mixture. It's enough. Okay. So the second question we got, pressure is 232.23, and the quality concept of 0.535, and this was a circulated mixture. And lawful we got 395.2, and the quality concept is not applicable. And for that temperature, this is even tough from those properties. This temperature is too high. Oh my god, you would literally be melting something. So this is superheated vapor. And here, this temperature is too low. You know, it says compressed liquid, and not applicable. And there was one. No. What was the internal energy? It was 313.99. And here we found our temperature is 172.94 and 731.00, and this is a circulated liquid. And your table is complete. You just finish your exam, right? If this was exam, you just finished it. And I hope I gave a precise explanation, and maybe you got some idea from this video. And I really hope I can see you in the next video. And I really wish you stick with me to do the learning process together. You know. So I'll be doing working out more examples, and I'll also cover the topic of energy analysis of closed system. So I'm still working on that, and yeah, once I do upload the videos, make sure you keep checking. Yeah. So the next video we do more examples, and we do the energy analysis of the closed system. So see ya.